Welcome to Sri Learning Academy. Let's simplify semaphores. Imagine multiple people trying to enter the same room through one narrow door at the same time. If everyone pushes at once, there will be confusion, collisions, and delays. The same kind of problem happens inside an operating system when multiple processes or threads try to access a shared resource together. That resource might be a printer, a file, a memory buffer, or even a simple variable. If access is not controlled properly, the result can be inconsistent data and unpredictable behavior. This is exactly where semaphores become important. A semaphore is a synchronization tool used by the operating system to control access to shared resources in a safe and organized way. It acts like a signaling mechanism that tells processes whether they can proceed or whether they must wait. To understand semaphores in simple terms, think of them as traffic signals for processes. On a road, traffic lights decide which side moves and which side waits, preventing accidents. In the same way, a semaphore coordinates processes so they do not interfere with each other while using common resources. Earlier, we discussed race conditions in critical sections, where multiple processes accessing shared data at the same time can create errors. Semaphores are one of the classic solutions to that problem. They help enforce order without requiring processes to constantly fight for access. Instead of chaos, processes follow a controlled system of permission. A semaphore is basically an integer variable managed through two atomic operations called wait and signal. Some textbooks may also call them P and V operations. The wait operation atomically decreases the semaphore value. If the resource is not available, the process is placed in a waiting state until it can proceed. The signal operation is used when a process finishes using the resource. It increases the semaphore value and may wake another waiting process. Because these operations are atomic, they happen completely without interruption. That atomic nature is important because if wait and signal themselves were interrupted, synchronization would fail. Let us make this practical with an example. Suppose there is only one printer in an office, but five employees want to print documents. If all five try to print directly at the same moment, pages may mix or jobs may clash. Now imagine a semaphore placed in front of the printer. Only one employee gets permission at a time, the others wait in line. Once the first employee finishes, the semaphore signals the next one. This is exactly how an operating system can protect a shared device like a printer. The same idea applies to software resources as well. You might be wondering how this differs from hardware locks or Peterson's algorithm that we explored earlier. Those lower level approaches often rely on busy waiting, where a process keeps checking repeatedly and consumes CPU time while waiting for its turn. A semaphore is generally a smarter and more practical coordination tool. Instead of forcing a process to keep spinning, it can work with the operating system to block that process and place it in a waiting state. The CPU is then free to perform other useful tasks. When the resource becomes available again, the operating system wakes the waiting process and allows it to continue. Now let us talk about the first major type, the binary semaphore. As the name suggests, a binary semaphore has only two possible values, usually 0 and 1. You can think of it like a switch that is either available or unavailable. If the value is 1, the resource is free and a process can enter. If the value is 0, the resource is busy and another process must wait. Because it allows only one process at a time, a binary semaphore is commonly used for mutual exclusion. In simple words, it helps ensure that only one process enters the critical section at once. Imagine a room with only one key hanging outside. If the key is available, a person takes it and enters. While that person is inside, no one else can enter because the key is not available. Once the person comes out, the key is returned. That key behaves like a binary semaphore. In operating systems, instead of a physical key, the semaphore controls access to shared memory, files, or important code sections. This makes binary semaphores very useful when one shared resource must be protected from simultaneous use. Let us take a coding style example without actual code. Suppose two threads are updating the same bank account balance. If both read the old balance at the same time and then write new values, the final balance may be wrong. A binary semaphore can protect that update section. One thread enters first and locks access. The second thread waits. After the first finishes, it signals the semaphore. Then the second thread proceeds. This prevents corruption of shared data and keeps results correct. Now let us move to the second type, the counting semaphore. Unlike a binary semaphore, a counting semaphore can hold values greater than 1. This means it can manage multiple identical resources at the same time. Instead of just available or unavailable, it keeps count of how many units are free. If the value is 3, then 3 processes can proceed before others must wait. Each successful wait reduces the count by 1. Each signal increases it again when a resource is released. Think of a parking lot with 10 parking spaces. If 10 cars are parked, the lot is full and the 11th car must wait outside. When one car leaves, one space becomes available. That available space is like a signal operation increasing the count. The next waiting car can enter. This is a perfect real-life model of a counting semaphore. It is especially useful when the system has several copies of the same resource rather than only one. Consider a computer system with 4 identical database connections available in a connection pool. Many processes may need access to the database. A counting semaphore can be initialized to 4. The first 4 processes get access immediately. The fifth process waits until one connection is released. When a process completes its database work, it signals the semaphore and another waiting process gets its turn. This prevents overloading the database and keeps resource usage controlled. So when should we use binary semaphore versus counting semaphore? Use a binary semaphore when there is only one shared resource or when only one process should enter a critical section at a time. Use a counting semaphore when multiple identical resources are available. Binary semaphore is about exclusive access. Counting semaphore is about managing quantity. Both solve synchronization problems, but the choice depends on the situation. Semaphores are powerful, but they must be used carefully. If a process performs wait and never performs signal, other processes may remain blocked forever. If semaphores are acquired in the wrong order across multiple resources, deadlocks can happen. If some waiting processes are repeatedly ignored, starvation can occur. These are deeper synchronization issues that we will cover later. So while semaphores solve many problems, careless use can create new ones. Modern operating systems use semaphore-like mechanisms internally in process scheduling, memory access, device coordination, and producer-consumer-style workflows. They are one of the classic foundations of concurrent programming. Even though higher-level tools like monitors, mutexes, and condition variables exist today, understanding semaphores helps you understand the logic behind all of them. So in the simplest possible terms, a semaphore is a permission manager. A binary semaphore manages yes or no access for one resource. A counting semaphore manages how many users can access multiple resources at the same time. When many processes need to cooperate, semaphores bring discipline and order. Without them, multitasking systems would quickly become unreliable. With them, processes know when to move, when to wait, and when to hand over control smoothly. That is why semaphores remain one of the most important concepts in operating system synchronization. That is it for this video. See you in the next one.